Okay, thank you very much. I appreciate the invitation from the Pennsylvania Vector Control Group. I'd like to talk about the introduction of the National Institute of Health and the National Institute of Allergy and Infectious Disease supported Black Fly Research and Resource Center. You'll see some new names associated with our laboratory. Dr. Daryl Batzer is the principal investigator on this project now. Dr. Danny Mead has done a lot of work with vesicular stomatitis and is with the veterinary faculty here at the University of Georgia. He's going to be the molecular lead on this project, and we will have some molecular reagents available for other researchers. And Dr. Ray Noblet is the longtime principal investigator. In the image here, you see Similium vittatum. This is the specimen that we raise in our colony, and that's their characteristic biting posture with their front legs elevated, their mouth parts embedded in some flesh. So that's a great image of a female black fly right there. Not all black flies are black, as you see. I think Doug mentioned that earlier. The females have a nice gray tint color to them. So, as many of you know, the University of Georgia Black Fly Rearing and Bioassay Laboratory has been in operation for a long time. We've participated in this meeting a number of times. I've done some work in Pennsylvania. I see Joe Iberg on the participating. He's a longtime collaborator of mine and did his graduate work in the lab and worked in Pennsylvania on larval feeding. So we've got a long history with Pennsylvania. We love you guys. We were for many of our years, we were a research and development site for Abbott Laboratories to start. That kind of ages us and dates how far we go back. And then Valent Biosciences. And from Doug Orr's presentation this morning, you could see that the economic times have been difficult for black fly work. The amount of ETI used in Pennsylvania, we're at a third right now from the peak. And the writing was kind of on the wall that there was going to be changes. And in 2017, we were informed that Valent was going to move their testing in-house and would no longer be supporting the lab. So I immediately began reaching out to our contacts, a whole career's worth of contacts for new work. We needed funding to help support the lab. And one of the names that kept coming up was Adriano Castero St. Denis of NIH. And we reached out to her after a year of communication. We were invited to participate or submit a proposal to the National Institutes of Health and the National Institutes of Infectious Diseases with a task order proposal entitled Black Fly Colony Support. And we felt really good about this since we have the only black fly colony in the world. We didn't think there was going to be a whole lot of competition. So we moved forward with this, and after some back and forth negotiations, we learned that we'd received a contract for black fly colony support. And this was a big relief for us. We've been 3 years with very modest commercial support, and there was concern that the black fly colony had been in operation since 1981. It requires a significant contribution of resources, and we were working hard to try to figure out a way to continue this operation. And the University of Georgia contributes significantly to this. They provide 1,800 square feet of quality lab space and the utilities that go with it, which everyone knows is a significant contribution. And they provide approximately half of my time. I still do a lot of work with this. I see a lot of you people out at meetings, but when I'm not out having fun at meetings and learning from y'all, I'm often doing some pretty routine work back here in the lab. NIH work support is going to provide part of my salary, a small portion, a half-time technician, undergraduate student workers, which have been a backbone of our operation for many, many years. The students often need lab experience. We often need lab workers. The colony is operated 365 days a year, so it's nice to have a team of workers involved. That's really one of the benefits of the whole operation here is that by doing it in the university environment, we can have a number of part-time workers. We can train a lot of students, give them experience they need to move on out and do better things other places and help us get through our work requirements. And then some operating expenses will be supported as well. So as a result of this new funding source, we're going to continue to produce black flies and provide them to anyone who's interested. And that's something we've been doing for many years now. And we will also serve as a research and education site. And the education aspect is something that probably goes a little bit under the radar. We have a number of classes that come out and visit the lab. We have high school students programs where they'll come visit the lab. So there's a pretty significant educational purpose and responsibility to the lab. When kids will come to the building here and they'll go over to the molecular labs and see the machines and see things like that. And then when they come to our lab, it's a whole different kind of step back in time to a very basic type of entomology that's not done as often as it used to be. A little bit of history for us. Dr. Ray Noblet was at Clemson University as insect physiologist. He was involved with black fly research since the early 70s involving leukocytozoan transmission in black flies. That's described as turkey malaria. And Bacillus thuringiensis was discovered in 1976, underwent a rapid commercial development. And he was in the literature, was contacted by Abbott Laboratories, and quickly developed a long-time relationship with them, evaluating their very earliest BTI formulations in the streams around Clemson. I joined the lab in 1985, and by 1989, we were conducting nearly 200 field evaluations per year. So we would go out, measure a stream, treat it at a low concentration, collect samples downstream, evaluate the mortality, come back the next day and treat the site upstream from it and evaluate it and compare the efficacy of different batches or test samples. But the need for a laboratory screening system was obvious. We couldn't continue that forever. So around 1990, we developed an orbital shaker bioassay. And when you put a flask of water on an orbital shaker, turn it on, it creates a current in the flask. And the larvae will gladly, black fly larvae will gladly attach to that inside of that flask to the clean glass surface and resume their filter feeding behavior. And it's become a really standardized and excellent system. Joe Iberg, again, published many papers on larval feeding and various components of the larval media. And we developed this initially with field collected larvae at Clemson. We could go out to the streams, get larvae, bring them back, do this. But it became quickly apparent that we needed a standardized test subject. So Dr. Ed Cupp had developed a black fly colony at Cornell. He had taken it to the University of Arizona. We got eggs in 1991 at Clemson, initiated the colony there, moved it to UGA here in 1999. And today we operate the only black fly colony in the world. It's Smelium vitatum, cytospecies 107. It's maintained in 9 aquatic rearing units. We produce about 300,000 black fly larvae in each unit. And the material from the colony is shared with researchers around the country for a wide range of projects. And that's really kind of what I'm getting to here is advertising the availability of this material. Just a quick view of the colony. These aquatic rearing units are the backbone of the system. The lower right portion of it is a 170-gallon reservoir. It's fiberglassed on the inside. We maintain these. I was fixing one yesterday. The water is pumped up to some upper reservoirs and flows down a trough. And this is the runway, we call it, where the black fly larvae develop. We've got 9 of these systems in place. This picture wasn't staged very well. You see the hose on the floor. We're constantly adding water. The food materials adds to them, raises the level in the tanks. We have to drain water out. You see floor drains here, important part. We will put some water on the floor from time to time. So just to look at the tank again, it has a pump down below, compressor here to control the water temperature. And when we see pupae on the runway, we cover it with these emergence hoods. And this is just lightly framed, pyramidal shape, glass funnel at the top. The adult flies migrate into the tubes and are collected this way. The real heart of it is here in the center where the water is pumped from the upper chambers over the lip, as we call it, and onto the runway. This upper portion of the runway is where the egg sheets were pinned to start the rearing. Each week we start a new rearing, so there's a variety of stages available in the laboratory. And some of these larvae here on this lip have washed off the runway through the pump and attached to this upper surface. And this is what we're looking to produce. It's just some nice uniform black fly larvae for larvicide testing is what our long-term purpose was. For those of you not real familiar with black fly postures and feeding, the larvae have large silk glands, will spin a pad of silk and attach the base of their abdomen to a surface where there's current flowing past. They twist. You can see how all these larvae have a twist to them, and they lay back in the current with their cephalic fans out and are described as indiscriminate filter feeders, just raking particles out of the water. You can see the midgut in each of these, and they're ingesting everything that comes by under 100 microns or so, digesting what they can, passing on through what they can. Studies show that they can clear this midgut in about 30 minutes. So the feeding studies are pretty easy to do in some ways. Again, just the emergence hoods, glass funnels at the top. See the lights across the back. They come on and off gradually on timers to simulate dawn and dusk. I don't think this is real critical now. We're 30 years into this colonization, but it's maintained. One thing has often been asked is, do we add genetic material, new material to the colony? And we don't. There's a risk of introducing pathogens, and it would be virtually impossible to measure the genetic input of a wild fly into this colonized material after so many years. So we still conduct research and temperature studies, repellent work, larvicide evaluations. Sophie Racy, our graduate student, is going to follow up with some of our research that she's conducting. We've always collaborated with interested parties, but it wasn't always an emphasis. Dr. Noblet, as a department head in a research university, always wanted us to focus more on research. We had a number of graduate students come through the system, postdocs and such, and less on being a supply site. This gradually changed as I demonstrated the value of our black flies to him, because we would be contacted by people and we can enable labs to do work that they couldn't do otherwise. Black fly populations come and go in the wild, so it's very difficult to go to a site with wild black flies and plan research experiments in that way. So if Scott Kranz wants black flies in Rutgers or New Jersey next week, I can have him there whatever day he wants to have them. So that's the beauty of the colonized material. We can get them out whatever you need when you need it, essentially. The colony is operated 365 days a year. We have all life stages are typically available each week. As I said, we have 9 units, so there's about 300,000 larvae. You do the math on that, we're over 2 million specimens in the laboratory right now. We can ship the freshly emerged adults is typically what we send overnight. We prefer to provide material and collaborate on scientific papers still, but we can sell material for financial support for the lab as well, whatever suits the needs of the companies involved or laboratories involved. Materials that are available, the eggs are easy to collect and ship. We have separate oviposition chambers where they deposit their eggs on pieces of cloth, but you must be prepared to handle them on your end, how you're going to hatch those eggs and rear the larvae. We've done work where you can rear them with stir bars and beakers, the orbital shakers, bubbler systems will all work, but you have water quality challenges that way. I think the flowing water in troughs seems to be the best way to do it, but it becomes a pretty significant involvement. Larvae aren't commonly shipped, although I have sent late instar larvae, put them on wet, moistened paper towels, seal them up in Petri dishes, and we can send them to Clemson, 80 miles up the road overnight, and they'll put them in water and they'll still be alive. So the larvae are much tougher than we realize. And you think about it, they're in rivers and streams, they're getting pummeled by particles during floods and things like this. So they do have to be a pretty rugged structure. And we weren't really sure that was the case from the standpoint that A lot of people were trying to rear black flies and having problems with it. And it turns out that it's probably more water quality and rearing conditions rather than actual the fragility of the specimens. Pupae can be collected from the runways, but they're not commonly requested. You're going to have adults pretty quick. They don't stay in the pupal stage very long, much like a mosquito. The adults are our most commonly requested material. They're easily shipped. They're hardy. We can send females if you just need females. Typically, we have a few more males than females because we're always kind of in the early part of the emergence. Even though with 9 tanks, they will run for 60 days. So it's just examples of the images and materials. Top right are the eggs. The individual strings are where a female has walked on that piece of cloth in the oviposition chamber and deposited her eggs. Light tan ones probably were not fertilized. The females will lay their eggs whether they're fertilized or not. We try to get as many fertilized eggs as possible. The larvae, again down here, the nice cephalic fans for the filtering apparatus. At the bottom here, you see the row of hooks that they hook into the silk. Anal papillae down here for osmotory regulatory purposes. On the left is the pupal stage. The larvae was attached here. They spin this silken cocoon. The respiratory filaments trail out the back, and a great image of the female Similium vittatum above. The eyes are separated, indicating the female. The male would have contiguous eyes across the top of the head. You can contact me for material, or material can be ordered through the Biodefense and Emerging Infections Research Resources Repository. That's BEI Resources. We're going to be listed on there, and this is a site that's supported by NIAID to provide research materials to the scientific community, and we're now part of that system. So we're very proud of that and glad to provide material and collaborate with anyone who's interested in doing black fly work. I thought this was a good opportunity to spread the word, and please just put us in the back of your mind if you need material, if you know someone who needs material, to contact me or the BEI Resources site. And in conclusion, I'd like to wish our friend and colleague Andy Kyle the very best in his future endeavors. I saw Doug had the same picture. This was off of my camera. This was Andy in his favorite spot with a Penn State t-shirt and waders in the North Branch of the Susquehanna. Andy, we're going to miss you, buddy, and we wish you the very best. So that's the end of my presentation. Thank you. Question.
There's one question. I don't know if you can see it.
Guys are colonized. I think you should probably contact me later. We have the full life cycle in our laboratory, and I'd be glad to talk to you about it in more detail. Have we tested residual granules for efficacy on black flies? Jeff, you have a hard time dissociating them into the proper particle sizes for the larvae to feed on. So if you can come up with that technique, we'd love to test it for you. Thank you.